Hello, Geography 212 class. Today we're going to take a look at Chapter 11, which is about severe weather, thunderstorms, and tornadoes. I'm going to divide it into two sections because there's a lot of material here. So the first section will be thunderstorms, and then the second section's going to be tornadoes. All right. Let's start off with what I call convective thunderstorms. They're also referred to as ordinary thunderstorms. These are rather small features. These are going to be thunderstorms that are very typical of the type we get during the southwestern monsoon. And you can see it's a three-stage occurrence. If we start with the first stage over on the left, it's called the towering cumulus stage. What's happening here is convection. The sun's heating the ground, ground's heating the air, and it's causing it to rise. So that's what we're getting. We're getting very quickly building cumulus clouds. In the second stage, called the mature stage is defined by rain reaching the ground. It's mature once rain starts reaching the ground. But if you look carefully at that slide, what you're going to see, or the middle slide there, what you're going to see is it's not just rain that falls out of these clouds. It's now a cumulonimbus cloud. Cold air is falling out of the cloud as well. And you can see it's traced by that dashed line there. And once that cold air completely covers the bottom of the cumulonimbus cloud, convection's cut off. Look at the third stage, dissipating stage. The dissipating stage results from all the cold air that's fallen out of the cloud, completely covers the ground underneath now, and just the cloud dissipates. This whole process can happen in as little as 30 minutes. Very typical of southwest Arizona or southwestern United States during the monsoon season. Now, what I've done is I've also put in a bunch of more information on each stage. You can go back and look at that yourself. I'm going to move on here. There's the mature stage. One of the things that does happen, though, that's important, if you take a look at this, this is Doppler radar over here. What we find is when this cold air falls out, it's like a cold front. We actually call them gust fronts, okay? But it's a small cold front. And look at if you look right along here, that is the gust front. And just like a cold front, as this cold air spreads out across the surface, it's creating lift in front of the front and can create convection, cloud development, condensation, and what we call secondary thunderstorm development. This happens all the time in Arizona, all right? Some of the types of clouds we can see out in front of those, shelf clouds. We don't get too many roll clouds around here, but we will get these shelf cloud that's indicative of a pretty strong thunderstorm. Okay, and then the dissipating stage. There is a thunderstorm classification system you can see here. We have what's called single cell. Those are the types I just described. Multi-cell clusters, we can get some of these in southwestern United States. A multi-cell line, these are going to be thunderstorms associated along a cold front in a line, as the name suggests. These can be pretty severe, okay? And then finally, the supercell classification, these are going to be the most intense thunderstorms. Typically, the whole cloud will rotate, and these are the type of cumulonimbus clouds that tornadoes can occur in, okay? So single cell, multi-cell cluster, multi-cell line, and supercell. Let's take a look at some of these. We've already talked about single cells. If you look at number 2, multicellular thunderstorms, there's two types that we'll take a look at. One is a squall line along a cold front, and the other is this interesting type called mesoscale convective complex. And yeah, either one can certainly produce severe weather. So let's go to that right now. Here is, if you take a look at this, going from about New Orleans into southern Mississippi here, this is going to be along a cold front. Again, this is Doppler radar. The color is indicating the intensity of the precipitation. Red is fairly intense. So this is simply a line of thunderstorms, probably some severe ones in here, along a cold front. Pretty typical in the southeastern part of the United States. But if we look over here, the multicellular cluster, look at this large cluster of thunderstorms. I mean, it's nearly the size of Arkansas. These are not that well understood. They tend to occur at night. and they don't occur along cold fronts. So a lot of research is going into studying these multi-cell clusters, okay, and they can be quite severe. Again, I've gone back here. No, I haven't. Gone back here. And again, you can get some more information what we just talked about. So have a look at this slide here regarding multicellular thunderstorms of squall lines in the mesocyclone convective complex. Now, so where and when do thunderstorms occur? First of all, we need humid air. Because what we really need to do, we need to get a lot of moisture up into the atmosphere to develop these cumulonimbus clouds. The second point down is we need atmospheric instability, so this maritime tropical air can lift. You know, the more unstable the atmosphere, the greater the lift we're going to get. And like I say, the third one down is a lift. Typically, for severe thunderstorms, this is going to be along cold fronts, could be along warm fronts as well. However, mountain slopes, orographic lift is certainly going to help. And, you know, if we get any kind of horizontal convergence of the surface winds, that can be a low pressure system. And finally, you know, the more humid the air, the less uplift we need to destabilize it and develop these cumulonimbus clouds. Staying with the where and when, you know, solar heating obviously is going to drive this atmospheric convection. But there are exceptions. If you look at the second bullet down, we believe there's a low-level jet stream that will occur up the Mississippi River Valley at night that contribute to these mesoscale convective complexes. So that's definitely one exception to solar heating, because these things will occur at night. Thunderstorm frequencies often expressed in thunderstorm days per year. So in other words, we're going to take a look at a map that shows approximately how many thunderstorms occur in various locations in the U.S. You might want to know, well, or you might ask, what is a thunderstorm day? All it is if we hear thunder, that's a thunderstorm day. If we hear thunder 100 times during the day, that's still one thunderstorm day. So here is the thunderstorm distribution in the United States. It's interesting. You can see that there are a few very active places in the U.S., and one is certainly down in Florida. We'll take a look at that a little closer in a second here. But you're also going to see that we have a lot of thunderstorms developing over central Colorado. Let's talk about Florida first of all. The Florida thunderstorms tend to be convective. In other words, due to solar heating. We'll talk about, like I say, I'll go into a little more detail in a minute. As you might suspect, though, we look over to Colorado, what would be the most prevalent source of lift there is going to be the Rocky Mountains, okay? You'll also notice that in New Mexico and Arizona, there's a high frequency of thunderstorms, particularly in the state of Arizona, at any rate, in the eastern part and the northern part, and that's due because of the lift. There's a lot of mountains in that area, and that causes lift and can create these thunderstorms. You can also, another interesting factor is you look along the west coast of the United States, there's very few thunderstorm days along the west coast of the United States. And the reason for that is because there's a cold ocean current that flows down along the west coast. This water comes from the Gulf of Alaska. The surface water is very cold. Cold surface water inhibits any kind of evaporation, so the air is dry along the west coast. And remember, that was one of the ingredients we need to get cumulonimbus clouds and then thunderstorms to develop. So we get very few right along the west coast of the U.S. So all that lift in the mountainous west creates a lot of cumulonimbus clouds. And then the heat that we get down in Florida. Let's take a look at that. So be a little closer at Florida. Florida is surrounded by very warm surface water in the ocean, okay? So imagine this. Sun comes up, it starts heating the interior because land heats up more quickly than ocean does. So we're going to start getting convective lift in the central part of Florida. Well, wherever we get lift, we create low pressure at the surface. Air wants to flow in to meet low pressure. And look where that air is flowing from. That air is flowing off of this very warm, moist air off the Gulf of Mexico or the southern Atlantic Ocean. So that moist air then gets caught in the lift in the central part of Florida, and cumulonimbus clouds develop. So it's a perfect, brewing ground for thunderstorms there in the state of Florida. Now, the severe thunderstorm scenario is portrayed by this surface analysis here, showing you a few things. Number one, we've got a cold front approaching. So this is going to be typically going to be continental polar air, dry, cold, dense air, moving into this maritime tropical air that's going to be quite moist. Now, something you see out in front of this cold front is something called a dry line, okay? What that does, it's separating the dry air over here in continental tropical air, it's dry, from the maritime tropical air here. Now remember, the difference between air masses can be temperature and or humidity. So in other words, the continental tropical air, the CT air here, is the same temperature as this maritime tropical air, but the big difference is moisture. So we develop a front. A dry line is basically a front. It's a front between two different air masses. In this case, the air masses are of different moisture content. So what happens then, if we do get a low-level jet, or any air really, flowing up along that, it's going to flow right up along the dry line, and this is where typically we're going to get a lot of lift, and this is where severe thunderstorms can occur. Some other things that can occur with thunderstorms. This particular photograph is of mammatus clouds. They will indicate that cold air is falling out of the top of these thunderstorms and forming these bulbous things underneath on the bottom layer of or at the very bottom base of the cumulonimbus cloud. When you see this, they generally indicate a severe thunderstorm. So you see this at the bottom of a cumulonimbus cloud. You can probably expect to get lightning and heavy winds with this. Speaking of lightning, what is it? Well, it's obviously a discharge of electricity. You can have within the cloud lightning, just staying inside the cloud. You can have one cloud to another cloud of lightning, and you can have cloud to ground, and that's the kind that we're most concerned with here. Only about 20% of the lightning in a cumulonimbus cloud is cloud to ground. What is it? I mean, it's extremely high temperature, as you can see, approximately 54,000 degrees Fahrenheit. So when this lightning is discharged through the atmosphere, you can imagine the instantaneous 54,000 degree temperature is going to cause an explosive movement of the atmosphere away from that heat. And that's what the sound of thunder is. It's basically this incredibly high temperature exploding within the atmosphere and causing the atmospheric molecules to very quickly move away. You can see here, I'm not really going to go into this. You can take a look at it, the different types of lightning, not overly concerned with this. One that I might mention, and it's really a misnomer, it's the third one down, called heat lightning. A lot of people say at night, will be out at night watching, and they'll see way off in the distance, they'll see lightning, probably just inside a cloud lighting the cloud up, and they won't hear thunder. And that's simply because the lightning is so far away that the sound dissipates by the time it gets to you. There's really, some people say it's a hot night. That's not true. Okay, I mean, it's still lightning. There is thunder if you're close enough to hear it. Okay. And this is steps in cloud to ground lightning discharge. Just an interesting one. We've really developed recently some high-speed camera work that can capture the whole thing on this. But basically what we get is we get this massive amount of electrons or negative charge near the bottom of of the cloud, and that's the first thing that hits the ground. It typically hits something high sticking out. These electrons go down there, and then what the flash of lightning you actually see then are going to be these positively charged particles moving from the ground up into the cloud. It happens very fast. That's why I was referring back to this high-speed camera work to see exactly how this works. So it begins with negative charge electrons coming from the cloud down to the ground, and then a very quick movement of positively charged ions back up into the cloud. And that's the lightning you see when the positive charges come back. Certainly a lot of hazards associated with thunderstorms. These downbursts, microbursts, wind shears, got all those names, but really it's a downburst, okay? Remember what I said earlier, that not only rain falls out of the bottom of a thunderstorm, but also cold air falls out. And sometimes this cold air can fall down at a very high rate of speed, a very great velocity. And we didn't really know about this until about 1985, when unfortunately a Delta Airlines, a Lockheed L-1011, was landing at Dallas. And on final approach, you can take a look at this diagram here. Would have been starting with the left here. On final approach, he saw a shower. The two pilots saw a shower in front of them, between them and the runway. But they just thought, we're just going to get a little bit wet here. Not realizing that coming in front of them was also this big downburst. So see what happened. The downburst hit in front of them. And look how the air spreads out. Initially, they got a headwind. Now, if you're in final approach in any aircraft and you get a headwind, that's going to force your nose up. And so you're going to push down on the yoke to try to get the nose to come back down. Well, look what happened. When he's in this position, pushes down on the yoke, and now he's right underneath the downdraft, pushing him down. And then even worse, he's flying into a tailwind, which is going to reduce his lift. And what happened to this Delta Airlines Flight 191 in 1985 was that it crashed to the ground at least a half a mile before the Dallas airport, and caused a fairly great loss of life. After this accident happened, we realized now that we can get these very high rates of downdrafts. And so now at airports that typically do get a lot of thunderstorms, we have put in wind indicators that measure the speed of vertically moving air. Now think about it. Normally when we give wind velocity, we're talking about the horizontal movement of air, right? So anyway, we've got vertical wind speed indicators in now around Dallas Airport and other airports that get a lot of these thunderstorms, so that this will not happen again. Now, if you're interested, go to the link. If you take this link, it'll take you to several YouTube videos that will recreate what happened to Delta 191, but I'll just leave that to you to follow up on. Other thunderstorm hazards, flash floods. We certainly get them in the Southwest when this happens. We're going to get, very rapid rise in stream level. And this can be a problem, as we see every year. People drive into these things. Again, I have a link to an incredible flash flood that came over Havasu Falls down in the Grand Canyon several years ago, but I'll leave that to you to follow up on. Okay, other hazards going to be hail. Hail is a piece of ice that's moved up into this cumulonimbus cloud and accumulated a lot of supercooled water droplets that freeze instantly on it. These things accrete, which means they simply grow by the addition of these freezing water droplets. And then when they get large enough, they'll fall out of a cloud. Right now, the record size hailstone in the United States is somewhere right around 8 inches in diameter. So you can imagine an 8-inch in diameter ice chunk falling out. It can do a lot of damage, and they do. All right, this is a segue into tornadoes, but I'll keep going here till we get right to tornadoes, and then I'll put part 2 in here in a few minutes. But supercell thunderstorms may have rotation. Okay, generally they do. In other words, that whole cumulonimbus cloud can slowly rotate. Now, the other thing that's important here, earlier on we were talking about these ordinary convectional and conventional thunderstorms that typically die off in about 30 minutes because all the cold air that falls out of them just smothers the bottom of the cloud. Well, take a look at this one here. This is going to be typically the setup along a cold front. So if we look here, as this whole cloud is moving from left to right, sure, there's a lot of cold air falling out from underneath it with the precip, but look, as it advances, it continues to get this steady influx of warm, moist air. So it doesn't get cut off from its source of warm, moist air as that cold front moves along. That's the difference between a thunderstorm that can develop into something quite severe, like a supercell, or just a convectional thunderstorm that will die off because it loses its source of warm, moist air. Also, you can see here, this is what we call the gust front. A gust front is simply a cold front. It's like a cold air coming out of the cloud. And remember, cold air will not mix with the warm air out here. A front develops. Now, another interesting thing that happens here, as this cold air comes down, let's say you're down in southern Arizona, it'll pick up what's at the surface, a lot of dust. The dust becomes entrained in this cold air. And remember, cold air isn't going to mix with this warm air out here. So the dust is entrained, and as this cold air flows out across the desert floor, in that case, you see a dust front, as it were, flowing along. These are called haboobs, and we'll get them when cold air falls out of a thunderstorm and picks up dust. All right, I'm going to end it here, and we will pick this up in part 2 when we do tornadoes.